Morning, Doctor. We are from SKE 2133, Section 7, Group 1, and my name is Yi Hong. Now I'm going to present our problem-based learning tool, which is the calibration and sensitivity measurement of lag-dependent resistor LDR. So now I'm going to start with our introduction of LDR. LDR is a photoconductive device whose resistance decreases with increasing incident light intensity. Then David will demonstrate about our PBL tool using the Arduino IDE to find the output voltage.
Good morning, doctor and my fellow friends. Today we are going to do an experiment. There are two objectives. The first one is to find out the relationship between the LDR resistance with the luminosity. The second one is to find out the sensitivity of the LDR. So let's get into the setup. So first we have the Arduino with the LDR module and also a light source. We maintain the light source about 15 centimeter from the LDR module. And let's look at the running code. So for the code, our LDR will output from 0 to 5 volt, representing the change depending on the change of the luminosity. So I'm going to demonstrate how we are going to record our value. Now, for this part, we are going to record the light intensity and our output voltage. So let us demonstrate on how to get our data. We have our light source standby, and then remain the light source at a constant intensity of light. So first we need to record how much is the intensity of the light, which in this case is about 2130. So now we are going to look at the serial monitor on the output voltage. So our output voltage is 0.49, and that's how we record our data. So after we record our first set of data, we can adjust the intensity of the light source. So for different intensity of light, we are going to repeat our data collection for a total of 10 times.
Next, after recording all the temp values of output voltage, we need to do the next part of this experiment, which is by using LabVIEW. So now David will demonstrate again how do we do the experiment by using LabVIEW.
Now we are going to repeat our experiment in LabVIEW. So let's look into this screen. You can see that this is our configuration for our LabVIEW. And then let's go and see our display. So it's running right now. Let's see our circuit. There's an LDR measuring outputting the voltage based on the luminosity. So right now, we can see that it's outputting 0.50 at a luminosity of 2020. And that's how we record our data for using the LabVIEW.
So this is our 10 output voltage values for Arduino IDE as well as the LabVIEW. And the resistance part can be calculated by using this formula, which R put out in our case is 10k ohm and the V reference is 5 volt. So finally the resistance of LDR is calculated out and recorded in this table. Next, we need to plot all the values in Microsoft Excel, which the y-axis is the resistance of LDR and the x-axis in the luminous intensity of light. And after that, we need to use Microsoft Excel to find the line of best fit, which in this case, both Arduino IDE and LabVIEW produce a second order curve, and this is the equation provided by Microsoft Excel. So the next step is we need to find the sensitivity of LDR by using this formula, which is change in resistance divided by the change in luminous intensity. And since we know that this formula is actually finding the gradient of both graphs, we can actually differentiate the equation to find the sensitivity at each luminous light intensity. So this is the equation after differentiate. The first one is from Arduino IDE and the second one is for the LabVIEW case. So for our case, we use 500, 1000, 1500 and 2000, and this is our final result, which is the sensitivity of LDR for Arduino IDE as well as the LabVIEW. So for the discussion part, the calibration curve, the resistance in both graphs decreased significantly with increasing light intensity, confirming inverse dependence. And for sensitivity, for both cases, higher sensitivity was observed at lower light levels due to higher gradient of resistance change. For the last part, which is the sources of error, variability in lux meter smartphone app readings. This causes inconsistencies in the output voltage readings, resulting in difference between the resistance sensitivity of both experiments using Arduino IDE and LabVIEW. A small change in the background light intensity level will also influence the result. And the next source of error is potential noise in analog readings, which also influence the final result of our experiment. And next, for the conclusion part, the experiment successfully calibrated the LDR and measured its sensitivity. The inverse relationship between resistance and light intensity was confirmed. The measured sensitivity provides crucial parameters for designing light sensing circuits. The sensitivity value of LDR is very important in our daily lives. High sensitivity in an LDR allows it to detect small changes in light intensity, making it suitable for applications that require precise light measurements such as light meters and smartphone brightness control. While on the other hand, low sensitivity of LDR also provide advantages in preventing false triggers caused by minor fluctuations, which is ideal for applications like automatic night lights and street lighting system. Different applications have different requirements on the sensitivity value of LDR, and the important thing is we need to select the correct sensitivity value for each of our applications in our daily lives. And that's all from us.
Thank you.